Okay, so the last thing I want to do is briefly mention how Gaussian processes can be used essentially for smoothing, like the non-parametric regression types of applications that we've seen in the past, like trend filtering and using wavelets. But the advantage of Gaussian process ideas is that they can be used in, when you're trying to smooth in more than one dimension very easily. So actually trend filtering and wavelets can also be extended to maybe more than one dimension, but Gaussian process can actually work in very high dimensions. However, we'll illustrate it just in one dimension because it's easier to visualize everything. But actually, you probably wouldn't use a Gaussian process for the one-dimensional cases, to be honest. So okay, so I've got my screen here. Yeah. So the kind of notes are here, and the vignette is, or the example is here. So let's just have a quick look at the notes. So the basic idea is that you can think of the y, I, a response in a regression, depending on covariates xi, as the yi is going to have some mean f of xi that depends on the covariates xi, and we're going to model f as a Gaussian process. So instead of using xb for some covariates x and linear function, parameterizing it linearly, we're going to use a Gaussian process to do it. And then, in fact, we'll see how, down here, we'll see you can actually think of it as a kind of a linear regression with a ridge regression. But just for now, just think about f being a Gaussian process. So the main point of f is that it will be, if the x's are similar to one another, close together in covariate space, then the f's will tend to be more similar. So this model essentially captures the idea that for those points where xi and xj, say points I and j, or data, subject units, whatever they are, I and j, for which xi and xj are close to one another, similar to one another, that is, they have similar covariates, they're going to have a similar value of y, or at least a more similar value of y. So that's the way of thinking about this. Okay, and so you can write, just it's a multivariate normal model for y, and so you can fit that just like you can use multivariate normals. It just requires you to choose a covariance kernel. So if we look at the example here, I did it for the cell cycle. This was trend filtering fit to those data, and this is a Gaussian process fit to the data as well. Actually, I had to get it to work on a reasonable time, I reduced the number of data points to 200 instead of 500 or so, I think it was. So these can be quite computation intensive because to fit a 200 Gaussian process to 200 data points, your covariance matrix is 200 by 200. And to work with covariance matrices, you usually have to do some kind of matrix decomposition, like a Cholesky decomposition, which grows cubically with the dimension, so 200 cubed, whatever. And so as n increases, these methods become very computation intensive, which is why you probably wouldn't use them instead of, say, trend filtering in this one-dimensional case, although you can see that the result is kind of, at least somewhat reasonable, right? But the nice thing about the Gaussian process is that even if you did it, if x was 500 dimensions, you would measure, instead of just measuring, the cell cycle example, imagine you wanted to predict a y based on 500 covariates, the way you might do it in ridge regression or lasso type things, but you want to do something that just captures this idea that things that are more similar in covariate space tend to be more similar in y space. The computation is the same, essentially, the same order of magnitude. It doesn't increase with p because everything depends only on the distances, right? So you just compute the distances with your p variables instead of with your one variable, and then the code becomes exactly the same. still cubic in N, I believe, but and there may be things that you can do. Well, there are things you can do to approximate the computations to make them more more reasonable for larger N. So the kinds of things people will do is essentially to assume that the covariance is banded, maybe, so that things that are a certain distance away set their covariance to 0 more than a certain distance away, or even block diagonal, that the covariance that essentially that corresponds to the idea that the observations cluster into groups that are correlated and then they're uncorrelated with other groups. And those kinds of things can be used to make the computation less than cubic in N. And I'm not going to talk in any detail about how those work. I don't think there's a single method that everyone uses, but there are many ideas out there to make them work faster. But I want to say a bit more about this basic idea. So how do we think about this in terms of maybe the eigenvector notion? So going back to the Dyno list here. So if we look at this this bullet here, you can think again in terms of the eigenvector representation. So if y is f plus e, you can write f, which is the Gaussian process, in terms of the eigenvectors of the covariance matrix, which are the VJs here. And then you can, I've written, instead of Z, I've written, before I had a ZJ here, the ZJ with the random weights, and the DJ here are the eigenvalues. So F equals VDV. Yeah. Sorry, the covariance matrix sigma is VDV. So I've written them as B here just to emphasize, instead of Z, to emphasize that kind of interpretation as regression coefficients. So you can think of this as a ridge regression prior on with the covariates now being the eigenvectors of the covariance matrix that you get from the GP. So actually you can think of all this as ridge regression. But with, so you can, instead of regressing on the wavelet basis or on the trend filtering basis, you're regressing on a basis that's chosen using the eigenvectors of the covariance matrix that you're using. Okay. All right, that's all I had to say there.